Hey, physics students, we're learning about momentum and impulse today. Momentum and impulse. This is the start of a new unit. And this idea of momentum is such a fundamental idea in physics, and you might already have some understanding of what this is. When you think about momentum, you hear terms like, hey, that team's got a lot of momentum. I hope they can keep it up into fourth quarter. Or you might hear actually something moving and they say, hey, it's got a lot of momentum. So what quantities do you think are involved in this idea of momentum? Is time involved? Is mass involved? Is acceleration involved? Velocity? What do you think makes up this idea? Impulse, well, that's the idea of impact or collision. So I think this is a pretty fun unit because we get into the idea of things hitting each other and the physics of that very small period of time. What's happening during that little period of time when things are colliding with each other and then either bouncing off or colliding and sticking. So very applicable stuff here. Let's get right into it. Roman numeral 1, momentum, what the heck is it? Well, I'm going to say its definition right here is, this is the verbal definition, a quantity associated with how difficult it is to stop an object, or to stop a system, we could say. So if it's really hard to stop something, then it's got a lot of momentum. And that's a good way to refer to it for people that aren't necessarily math people. Quantity associated with how difficult it is to stop a system or something. So what about a semi-truck? What about a baby carriage? What about a bullet? How easy or difficult is it to stop any one of these items, right? Obviously, we know the answers to those three examples. And I'll come back to those in a second. We'll see something interesting. This is the mathematical definition of momentum. Momentum is the product of mass and velocity. So in order to have a big or small momentum, you need to affect one of these or both of these. And when I say product, it means multiplication. So here's my equation that goes along with this verbal statement. P, lowercase p, is momentum. And momentum is equal to mass times velocity. It's that simple. All right. Just like net force is equal to mass times acceleration, a very simple equation. This one is a very simple equation also. P, momentum, is equal to these two things, multiplied. I think you know that's mass and velocity. I'm not going to write mass and velocity under that, but I am going to ask you, what is the unit of this thing? The unit, it doesn't have some fancy name like force had the unit of a Newton. What's the unit of this thing? Well, let's look at what mass is. Mass is kilograms. And what's velocity? It's meters per second. So your unit for momentum is the kilogram meter per second. And there's no shorter name for that. That's what we use as the standard unit for this idea of momentum. Last thing to say here, momentum is a vector, meaning it has a magnitude and a direction. The good news for you guys, we've been doing vector addition. We've been looking at angled forces that we have to break into components, angled velocities that we have to break into components. With this unit of momentum in CP physics, we only do one dimension. We do not do two dimensions, so there's not going to be any angled momentum problems. Although, if you went on in physics, you would definitely do angled momentum problems. I mean, you probably experience this all the time. Have you ever played a game of pool, right? You hit the cue ball at one of the other balls, and it doesn't hit it straight on all the time. It hits it like this, and then they both glance off at angles, and now you're dealing with a two-dimensional momentum problem. But we will only look at one dimension. So it's a vector, meaning it has a magnitude and a direction. All right, cool. Let's come up with a ridiculous question. Which has a greater momentum? A truck or a baby carriage? A truck or a baby carriage? I was just thinking, I don't know if I know how to spell carriage. I think that's right. Truck or a baby carriage. So we got our big semi truck here, the big grill, and it's got its big headlights here, Optimus Prime, right? And there's the hood. There's the wheel well right there. Okay, and then you go down the freeway and you go, and then they go, and they honk it for you and get all excited like you've never heard that noise before in your life. I never do that, Mr. Heinrich. Okay, sure. All right, so there's your big semi truck I was talking about, kind of quickly drawn, right? Well, that's very narrow, isn't it? And here's our little baby carriage. Oh no, no, what are you doing, Mr. Heinrich? Is the baby going to be okay? We will see. Who has greater momentum is the question. Who has got the bigger momentum? We got some handles on here, right? Mom is obviously off at Starbucks drinking coffee, doesn't even realize where the carriage is. Who's got the bigger momentum? It's the showdown of the century. Well, the real answer is you have no idea. You have no idea unless I give you more information. Of course, your gut tells you this thing's got more momentum, but what if this thing's velocity is zero? If this has a zero velocity, it's got no momentum. According to the equation, mass times zero would be zero. So it's got no momentum if its velocity is zero. And what if the baby carriage is going like at the speed of sound, right? You could have a tiny little mass of a baby carriage, but a huge stinking velocity, and you would have a big momentum. Now that idea should make a lot of sense to you. Think about a bullet. A bullet's got a tiny mass, but an incredible velocity, and therefore it has a huge momentum. So what's the answer? It depends, right? It depends. But we can pretty much say this. But if the truck has any velocity at all, has any velocity at all, it will likely have a greater momentum. I mean, it will. Right? Okay. Done with that. Hopefully you didn't take a full page for that. I know I did. Let's go on to the next idea. So that's the idea of momentum, but let's introduce this idea now of impulse. Impulse, impulse, impulse. I know what those are. Those are those emotions I get, and then I act on them right away before I think. Well, yeah, that's an impulse too, but this is different. This is the physics version of impulse. And what are we going to say? Well, let's give you a verbal definition on this too. A quantity associated with collision. With collision. And really, I'm not just going to tell you the equation, we're going to develop it. So developing the impulse momentum theorem. Theorem. There we go. And right up here, in fact, I'm not just going to call this section impulse. I would call this Roman numeral 2. This will be the impulse momentum theorem. All right. So we're going to go back to an idea that we've already learned about and we've done a lot of work with, which is Newton's second law. So let's start with F net equals ma. Now that was not his original version of that law, believe it or not. His original version of that law was F net equals mass times this. What is that? Well, if you go back to the very beginning of physics in your notebook, you'll see that the very definition of acceleration is a change in velocity with respect to a change in time. So this is just the definition of acceleration. So I plugged it in for acceleration. Delta V is a change in velocity with respect to a change in time. That's what it means to accelerate. We're changing our velocity, either making it bigger or making it smaller from what it used to be. This was closer to his original version of the second law, but let's make one more change. I'm going to make two changes, in fact, and we're going to box it. I'm going to do F with a bar over the top. I'm not going to call it net. I will tell you what that means in a second. I'm multiplying delta t over to this side, so multiply both sides by delta t, and set that equal to m delta v. This is the impulse momentum theorem, also called the momentum impulse theorem. It just depends on which book you look at. So this is impulse. This idea of force times the time is impulse. And what in the world does that look like? Well, we just discussed that, but it's a little different, right? We just discussed, hello, momentum, which is mass times velocity. This isn't quite mass times just velocity, it's mass times change in velocity. So what is this? This is the change in momentum. And this really was the original version of Newton's second law. It just turned into that, because it's also called the impulse momentum theorem. All right, so let's say some other things here. Then what's the unit of this idea of impulse? Impulse is equal to F delta t, and its unit is the Newton second, right? Newtons times seconds. Well, change in momentum, the unit over here would be kilogram meter per second, right? So the point I'm making to you is these two units are equivalent ideas. So the Newton second is equal to the kilogram meter per second. And you really could use either one to talk about momentum or impulse, and you would be correct. Typically, we use the Newton second for impulse, and typically for momentums, we use the kilogram meter per second. Oh, okay. Let's talk about this little hat on top of the force. Anytime you see that, it means average. So this is the average force. Average force. And remember what I told you about impulse. It has to do with collision. So this time we're talking about is an incredibly short time usually, because this equation helps us figure out how to explain collisions. There is an average force that's acting during a collision for a very short amount of time, and that impulse will change the momentum of a system. Here's a great example. How about hitting a baseball with a bat? The time that the baseball is actually the baseball bat is in contact with the ball is a very, very short time. We're talking about milliseconds, 0.003 seconds, very short amount of time. But there's usually an incredibly big force. But the thing is, that force is kind of changing throughout the hit. I want you to think about this with me. Here's the bat coming in. Let's make sure you can see the ball, right? This is the ball. And when the bat hits the ball, at first it's barely putting any force on the ball, right? But then in the next moment, if you had a slow-mo cam, you would see the ball begin to compress. And so the force is now much bigger, and then the ball gets this maximum compression as the bat is swinging through, and the force is even bigger still. And then as the ball comes off the bat, let me remove the bat now, the ball begins to reform itself back into that circular shape. And so the force begins to diminish as the ball leaves the bat until there's no force. So through that explanation, I hope you can understand that if you're looking at the force, it starts at 0, then it spikes, and then it goes to 0 again. So you have this changing force throughout a very short time, right? And therefore, since the force is changing, we have to look at just the average force. Let's draw a picture of that. So let's say, suppose a ball is hit by a bat. How would we graph that? Well, we would put the force here, and we would put the time here. And so I'm going to basically draw what I just explained to you without explaining it all over again. You would get this very, curve out the top a little more for me, kind of like a bell curve like that. Yeah, just like that. That's what you would see. There'd be practically no force when the bat was first coming in contact with the ball. Then when there was a maximum compression of the ball on the bat, you would have a maxed out force. And then as the ball left the bat, the force between the ball and the bat would drop off to zero again. Now, unless you're doing calculus, you can't deal with these instantaneous changes in forces. We are in algebra-based physics. And so the best we can do is use the average force, which is why that's there. Now I'm going to continue with this little picture, and I want to also say here, time is very small for most collisions, right? Something I already said, but we want to write in our notes. And we want to say here, force is changing throughout collision. And this is how we would express those two ideas graphed against each other. And this is in newtons and this is in seconds right here. We will always want to label our axes with quantity and unit, quantity and unit. Now again, you don't know how to find the area of that. Now why am I talking about area? Because the area that I just shaded in, area equals the impulse. The area of this force versus time graph is the impulse. Think about it. Area is a product. Area is a multiplication. Go back to your first math class. Base times height, base times height. Isn't that what an area is, right? And what are we multiplying here? Time and force. When you multiply those two, what do we call that? Impulse. So shouldn't it make sense that the area, which is a multiplication of force and time on this graph, is the impulse? I hope that made sense to you. If not, just memorize it, okay? The area of an FT graph is impulse. And again, we don't know how to find that. So where am I going with this? You're like, yeah, you keep saying that. I know, but I need to make sure that you're tracking. So we're dealing with the average force. Hello. So out of all of these forces, all the way from 0 newtons to, let's say that this is, I don't know, 4,000 newtons. It's a pretty big force that hits a ball with a bat. What's the average of that? Wouldn't it be 2,000 newtons right through the center? It would be. So this would be 2,000 newtons right here. I'll write that there, 2,000 newtons. And now if I find this area that I'm about to shade in blue, is that pretty much the same area as the black area that I shaded? Yes, it is. And that's why we can use the average force in a collision, because if you can just picture this with me, if we were in class, this would be so much easier. Picture this with me. This blue rectangle is roughly equivalent to this bell-shaped area. Because if I took this little piece right here, and I took this little piece right here, and I turned them and went, don't you see how that right there is pretty much that? And how this right here is pretty much that? Yes. You can see now that if I just turn these up, that fills in that space very well. So this blue area is a very good approximation of the impulse during any collision. So let's make that final statement. This is probably the hardest part of the notes. Okay, so if you have questions about this, please ask me after Zoom sometime and I'll explain it again. So I'm going to say here, if the average force is used, and the area taken or calculated it is a good approximation of impulse. If the average force is used in the area taken, right there, it is a pretty good approximation of the impulse, which again, remember, is this black shaded region right here. That blue shaded region is pretty much equal to that black shaded region. And we find that blue shaded region by using the average force times that time. Now I'm kind of putting the cart before the horse. I got off on this tangent about impulse, which is very important. But what does an impulse do for us? It changes the momentum of a system. And you know for sure it changes the momentum of that baseball. That baseball's coming in one direction, and now all of a sudden it's going the other direction, probably even more quickly than it got pitched in. We change the momentum of that baseball greatly by implementing this impulse with our baseball bat. So let's do a problem. Let's do a problem and get to the bottom of using this new equation called the impulse momentum theorem. Example time. So let's see here. Let's just stick with that. We'll say a baseball bat hits a baseball of mass, let's say it's 0.5 kilograms. I'm not sure what the actual mass of a baseball is, but that sounds good. Baseball bat hits a baseball of mass 0.5 kilograms, changing its velocity from, let's say 40 meters per second left to 50 meters per second right. That's good. A, what is the impulse delivered to the baseball? What is its change in momentum? And then there's going to be a part B, but let's finish part A first. Let's write our new equation. Actually, we could write some givens if you want to. We have a mass of 0.5 kilograms for the baseball. We have a VI, initial velocity, of 40 meters per second left. Now we're in one dimension here. Everything's happening along the x-axis for the most part. And so again, here it's very important that we call our velocities negative or positive. So we're back to that idea like we were in kinematics where we have to call these negative or positive. So this is negative 40 meters per second. And VF is going to be 50 meters per second. And I want to know, what is the impulse? Well, impulse doesn't have like just a variable, right? Like force is F, momentum is P, right? But impulse doesn't have a fancy variable. We just have to write F delta T. That is the impulse. And what do we know that impulse is equal to? Well, obviously it's equal to force times time, but we kind of use this also as the variable. Does that make sense, right? So if that's confusing you, that's fine. I'll cross that out. I could write impulse, imp equals F delta T. That's fine. Let's write that. Do you know force? Do you know time? Is that even given? No. So can you use force times time to find impulse in this case? No. But what is F delta T also equal to? Well, according to the impulse momentum theorem, or the momentum impulse theorem, it can be called either. Impulse is also equal to m delta v, and we do have that information right here. So based on that, I can say impulse equals m delta v. What's m? 0.5 times what? Now remember, a delta V is a V final minus a V initial, right? That's what a delta V is. So I have to actually go in here and say, okay, well, it's 50 meters per second minus, because the delta has a minus in it, right? That's always there if you have a delta, minus a what? A negative 40. Negative 40 meters per second. And look at that, it produces a positive for us. So we have an impulse of 0.5 times 90, right? 50 plus 40 is 90. And we have a 45. Now, what was that unit I told you to use for impulse? Newton second. Or you could say the kilogram meter per second, but honestly, this is probably the more appropriate one to use. There's my impulse. Done. But I also found my what? Change in momentum. Isn't my change in momentum m delta v? That's what I just plugged into. So this is also equal to m delta v, which is the change in momentum. All right. So when you find one, you found the other. They're one and the same. Now the next part, part B, is this. Part B is if the collision takes, let's say, 4 milliseconds. That m means milli, that's 1,000th. What is the average force? Acting on the baseball. Now we know that force is all over the place. When the bat first hits the ball, it's barely exerting a force. Then all of a sudden, in a very short time, there's this spike in the force. And then as the ball leaves the bat, that spike comes back down to 0 newtons. So there's this huge change in force, this fluctuation that happens. But through that fluctuation, what's the average, right? And that's what we're looking for. Let's find the average of that spike that occurs. Well, that's not too hard to do. What else is impulse equal to? It's equal to F delta T. So I could say F delta T equals this answer that I just found for impulse, right? 45 Newton seconds. And now I could divide both sides by delta T. So let's rewrite this to say F, and this is an average force, right? Average force times, this is really important, you don't miss this. 4 milliseconds is 0.004 seconds. Just like that. 1, 2, 3. Right? That would be, this is the thousandths place. Milli means 1,000th. So F times 0.004 seconds equals 45 Newton seconds. And now we're going to divide both sides by that 0.004 seconds. And look, the seconds cross out. What do you know? And you're left with newtons. So let's do our division. 45 divided by 0.004. And we get a humongous force, way bigger than the one I talked about in my graph. We get 11,250. Now we're starting to get to that area of physics where it would be helpful to express things in scientific notation. I don't want to go through a whole lesson on that right now, but I want to remind you that even though we don't write it, there's a decimal there. And if I move that decimal 1, 2, 3, 4 spots to the left, then I have to increase my power of 10 4 times. Now, why did I stop there? Because I got to a number between 1 and 10. So you move your decimal till you get to a number between 1 and 10. Stopping there gives me 1.125. And really, if I was going to write this, I'd probably write 1.13. I'd round it up, but I'll go ahead and write that. Times 10 to the 4 decimal moves means 10 to the 4th newtons. And that's just typically how the science community expresses very big or very small numbers, is with scientific notation. But I would accept either answer, of course. 11,250, or that one is fine. All right, so you can see that's a tremendous force, and that's just the average, right? That's just the average force acting in the baseball. So if you multiplied this by 2, that's probably the max force that happens on the baseball when the bat has fully compressed that ball. It's an incredible amount of force. Now, again, my values might be a little off from actual values, but it's actually, I think they're pretty close. You have really, really big forces and very, very small times when you're dealing with a collision. And now we have physics that actually helps us understand and calculate quantities that are associated with collisions, which is pretty neat because there's a lot of collisions out there. You might be talking about a bowling ball hitting pins, a car hitting a car, right? There's in everyday life, there's always collisions. Your girlfriend slapping you in the face because you said something insensitive. All kinds of collisions, right? A brother socking a brother in the gut when he's not looking. I know you know what I'm talking about. Okay, there's a problem. We've been at this for a little bit. There's definitely more to these notes, but I'm going to call it here, and we'll see how many pages that took you, and you can tell me, and then we're going to add on to this because we have some conceptual examples to look at for impulse. For instance, if someone's going to punch me in the face, right? If I'm a boxer, or if I just got in an unfortunate situation and I'm in a fight, would you A, run into the punch, B, take the punch, or roll with the punch? Which one of those would you do? Well, I would just get out of the way. I'd dodge it altogether. Okay, good for you. But if one of those 3 things had to happen, into the punch or roll with the punch, which of those 3 hurts the most? Which of those 3 hurts the least? This equation can tell you. If you're playing a sport, follow through is huge in almost every sport. If I'm shooting a basketball, I want to follow through. If I'm driving a golf ball, I want to follow through. Certainly with a baseball bat, if I'm not bunting, I want to follow through. If I'm catching a ball, I want to go with the ball like this if I'm playing water polo, right? This equation can tell you why you follow through in sports. So that's next time. We're going to look at some conceptual examples that surround this impulse momentum equation. I did remember one more thing I want to do. You're like, no! Oh well, deal with it. I want to look at a couple more variations. So I'll put another bullet here and I'll say variations of the momentum impulse theorem. And see, there you go. I went ahead and I called it momentum impulse instead of impulse momentum. I'm fine with either. Let's start with the one we know, F delta T equals a change in momentum, and m delta v. Remember, momentum is mass times velocity. Keep that in mind as we go through this exercise. Well, underneath this, I'll write F delta T. That's pretty much always going to stay the same on this left side, equals mass times, and we already did this, Vf minus Vi. There's one version of that. Well, now let's distribute our mass to both of these, and I would get F delta T equals mVf minus mVi. I would distribute my mass to both. Hey, what is a mass times a velocity? What is a mass times a velocity? Oh yeah, it's a p. It's a momentum, right? So an mv is a p. So I could write underneath this F delta T. Again, this side is the impulse. This side is the change in momentum, equals PF, because mv is a p, minus a pi, right? And what is any final minus any initial? I don't care if it's final velocity minus initial velocity, if it's final time minus initial time, if it's final banana minus initial banana. Anytime you have a final minus an initial, you're talking about a delta. So your final version that you could box would be delta P. And actually, I like that version because we're talking about the impulse equaling the change in P, or momentum. So any of these variations are useful depending on what they give you in a problem. So there you go. We're going to talk about those conceptual examples later. Have a great day. And if you have questions, especially about that graph that I discussed, let me know. Have a good one.